I might not have. I was writing quickly. Trigono. Oh, I'm missing an O.
Yeah, I'm not spelling either.
After me either, so that's why I say May.
Trigonometric. Here you go. Okay. Hi, Joyce and Jackie. The kids in class are writing down these notes, so we might need to come back and pause it if we don't take enough time on it. But I'm going to show you what we were doing at the beginning of class. Remember, Forever Endeavor quiz quoting technically is supposed to be due today, as in Wednesday, but I'm not going to collect it until tomorrow, just to give a little bit of grace. People still working, same thing as the bonus exam. So both of those are due tomorrow. And there's going to be a baby quiz tomorrow, but I'm actually having you guys make each other's. Jackie, don't worry about it. George made 2. So you're just going to take whoever's you get tomorrow. And there's one for you, if that makes sense. And then Joyce, I have a blank piece of paper for you. George didn't want to waste a tree, so he has an extra piece. And you just need to have question number 1 be a Calc AB fill-in. Just like a quick answer, derivative formula, something like that. The next 2 are going to be CalcBC fill-ins. It could be answering a formula. It could be stating, mostly formulas. Those are good fill-in ones. I was mentioning logistic. I was mentioning integration by parts, stuff like that. Short answer is something where you're just pulling out or asking about one part of a card, not the entire card, just one part, like state the formula for the limit definition of a derivative. That's like just one part of the card. Or like how do you find an equation of a tangent line, or given f is continuous and f prime is positive, then what's f doing? It's kind of short answer, kind of fill in, but either way. And then the one theorem or definition is how to end, and it's just like state IVT, EVT, MVT, roles, definition of continuous, etc. It's just something where it's basically like state the entire card. Make sure it's something that's that makes sense to state it all together. Don't do something silly like problem-solving clues for motion, which would be awful. All right, so I'm going to have you fill that out, and then tomorrow you're going to take a little quiz on it. Okay. Right now, this section, we're just calling it the aside because it's not on the AP Calculus BC exam, but it is something that almost all Calculus 2 classes in college cover, and it could be necessary. It's like you don't need it until you do. Some random integration or physics problems, etc. might only be able to be integrated by hand with trig substitutions. I'm just going to show you guys how to do it so that you have it in your notes. And then tomorrow we'll really start on Chapter 9, Section 1, if everything goes well and my foot hangs in there. Okay, so the rest of you guys, you're writing down notes?
I'm done writing down notes.
What? Go team. And we know we're turning in for tomorrow? The worksheet in front of you. Oh, yeah, Joyce and Jackie, there's a worksheet too. I think it's saved in the class folder. Let me check real quick. It's finishing for homework. But if you notice it, are there 2 pages of problems? No. Oh, right here. It is on the shared folder, you guys. Jackie, if you want to print it out and still do it, it's the trig substitution practice problems. One side is the problems, and the other side is, ooh, that's exciting, right? And then technically, if you look online, ooh, the first half are all solved. Now, technically, I don't want you guys to do all of them. All of them will just say odds. Sound good? But for the first half, the sample problems, all the solutions are worked out online. I didn't give you guys the copies of all that because you can just go online and look. Sound good? Only odds. Only odds. No, thank you for making sure. Okay, so coming back to, there we go, the aside. Here's the dilemma. What if you have any of the following expressions in an integral without a du? What do I mean by that? Not without a du, but without a corresponding chain rule supplement? Additional piece that would allow you to make the entire under square root part be a u, u, a v, or a w.
There for a second.
You know what? This will be a good idea. This. What if you have a square root and it's not in the denominator, and there's no additional piece to allow for you to make the entire argument of the square root into a function with the corresponding u prime.
Then you have a big
Or
problem.
v prime. You have a big problem. Yeah, you have to use trigonometric substitution. But do you guys see why this could be useful? Now, technically, depending on the form, might you be able to think about it as a circle? Wait, a circle, what am I talking about? A half circle. Why? What's the square root of r squared minus x squared? It's positive, it'll be the top half of a it'll be a semicircle with a radius of r, the positive area, right? And if it's a negative on the outside, well then it would be flipped, obviously. But it has to be of this form. So which of these could we maybe think about as a half circle and do 1/2 pi r squared? This first one, right?
Well, why can't we do all of them?
Well, because if you have the equation of a circle, x squared plus y squared is r squared. In order to get y squared by itself, you have to have subtraction, so addition doesn't work.
Can't we have like negatives?
And in the other one, if it was negative, then the function would be negative. Hold on. So u squared would be like your but you see, when you move the constant, the variables would have different signs, so that wouldn't be the equation of the circle either. Okay. However, each of these three can also be solved with something that we call trig substitution. How does it work? You ready? Clues. Stick to substituting in sine, tangent, and secant. You'll see why in just a little bit. Stick to plugging in sine, tangent, and secant. Set up a triangle. Use the triangle to solve for x. Find dx and basically plug each other. Let me give you guys a second though, because this is just the process that we'll have to figure out how it works with the examples.
I think Mrs. Johnson has one of those smart board thingies, like the portable ones. So you'd be able to sit down and ice your foot while you're teaching.
Pretty helpful. I won't take it away from you. It's okay. Can you do it at your computer?
You just can't really try.
It's okay. This thing's really pretty.
That's true. Or you can have one of us draw you.
True. Might be a bit of a struggle. I was feeling better earlier, but now it's hurting.
Don't take sediment.
Why?
It keeps the swelling going and then it makes it food.
Don't take medicine or do?
Don't take acetaminophen. So like Taiwan. Yeah. Take ibuprofen or Advil.
Can you go get the Advil out of there? And then my water's on my desk. Thanks, bud. I meant to do it earlier and then just hasn't looked fun going back to my desk. Should be. Thank goodness for kids not taking their drugs in senior retreat. No, this was grad night. That's what this was.
Grad night.
Because you're not allowed to have stuff, and so they'd all give it to me.
Wait. Why did they do Advil?
They just had it in their purse or whatever, didn't want to throw it away.
Is it
2
really
or
sick
3.
with drugs in
I'm
it?
thinking 3. Huh?
They really took them for drugs and everything?
Mm-hmm.
Wait, 3 Advil? That's a lot.
The little ones, not the big ones.
I would say.
I always get 3.
I would
That's
say.
a lot more than 3.
Yeah, because ibuprofen, I get like the gram size one. I get like 2 of those now.
Second semester started with a bang.
Yeah.
Boom,
You
crash.
broke your foot, I'm out of your locker.
Hey, you know what?
I woke up late this morning.
Adventures all over the place.
I got Starbucks because I woke up early.
I know I got here early and I got stuff done. Oh well, Lord's in control. Okay, so do we have it now?
You can explain what angle restrictions are.
Which one?
Angle restrictions.
Yeah. It's more of an example thing, so we'll just hang in there.
Is that like tangent of pi over 2 does not exist?
Yeah, kind of. Or if there's some sort of natural restriction built into the integral, because there are going to be bounds. And since there are bounds, it might restrict, because we're going to transform from being in terms of x to being in terms of theta. And so the x bounds need to be transformed to theta bounds, and so we just need to think about those restrictions. Does that make sense, kind of like with u bounds? Okay.
No, it stays the same, it stays the same. Because the -1 you just plot everything like that.
Okay, how do you make this person?
No, and it's just.
But so I should be able to drive. Okay. Okay. Here is like a quick summary. You guys don't necessarily need to write this down. I mean, it might be good for you to have, so if you want to take a picture, print it out, or paste it in. I don't know if you necessarily want to write it right now because we don't have a lot of time. But let me show you the idea, okay? This is what's stuck in your integral, yeah? That you don't know what to do with. This is stuck inside your integral. However, this could have come from a rearrangement of the Pythagorean theorem of a right triangle. Why? Pythagorean theorem, a squared plus b squared is c squared. And if you solve for any one of those sides, you're going to have a square root of something squared plus something squared or something squared minus something squared. Does that make sense? So we can take this as an application of something to do with the right triangle. So when we look at an integral, this is in there. There's no other way of dealing with it. It's not in a denominator. We can't use inverse trig. It doesn't have like a corresponding chain rule component that could let us just do a simple chain rule backwards. Then here's the strategies for how to deal with each of these different cases. If you have, now a is a constant, right? If you have constant squared minus variable squared, you're going to want to use sign. Why? Because then you can make your variable be the opposite. You can make your constant be the hypotenuse. And then this little piece, which is the part inside the integral, would be the adjacent. Because you would do hypotenuse squared minus side squared. Now this isn't solving the problem, but this is letting you know how to go from the problem, because then you can say, who is this in terms of the problem? Well, in terms of the problem, I could say this one adjacent over, well, to go this way is going to be complicated. It's a variable expression, but to go to the hypotenuse to use cosine, it would just be cosine, but with a multiple because of this constant that the hypotenuse is. So I could substitute from this to this. I can integrate that. Let's go. For this one, since I have a squared plus u squared, the easiest thing to use is tangent, because I can make a be the adjacent, u be the opposite. My hypotenuse will be the square rooty thing, my expression from the integral. I can say, hey, let's take this hypotenuse, let's take this, which is my constant, and let's say, hey, we can make secant out of that. So I can move that a to the other side, I can plug in for a secant and go. Similarly, this one, if I have the expression first squared minus the constant squared, then I could go ahead and have the constant be, once again, now, guys, if you notice, as much as is possible, we have the u be the opposite, and as much as is possible, we have the a be the adjacent. Then we can go ahead and plug in and solve. Now, let's take an example then. And this is probably as far as we'll get today, which means this won't be due until Friday. But that's all right. I think it's still worthwhile, and I was Googling and looking around online, and random integrals can show up later in math, whether differential equations, linear algebra, physics, that might need this. I just don't want you to be handicapped because we don't go over it. Okay? Let's go ahead and take this example. Okay. Why not inverse trig? Oh, wait.
US is first.
Yeah, for arcsecant, I need this one to be first, and I need this to be the u prime, or just the u, sorry, just x, not x squared, right? Partial fractions, no, that's a square root. Well, what do we do? Okay, trig sub. If you guys look on or think about that page before, if we have constant squared minus u squared, as much as is possible, we make the constant that's been squared the adjacent. We make the variable the opposite. Oh, but wait a minute, minus. Can I make this the hypotenuse? No, that would be plus, right? But I can make it be the opposite. Do I have the right one? Oh, I switched it. Sorry, it's supposed to be sine. This is a not possible one. You tell I'm rusty on it. Lo siento. This one is your x. There we go.
You're really neat with this.
Trying. Okay. And now we say, how can I substitute 4? Well, if I look at this expression, I don't want to compare it to x. I don't want to go over x because that's not what I have here. But I could maybe go over 3. So, okay, I have adjacent over hypotenuse. So I could say that 3, multiply the hypotenuse up, cosine of theta is equal to the square root of 9 minus x squared. So right now I'm looking at, okay, I could put a 3 cosine theta right over here, right? And similarly, if I have over, then I could go ahead and even make it secant if I wanted to go that far, and we will in a second. But how do I do x squared? What do I do there? Opposite over hypotenuse. Yeah, I could do sine of theta. I know, I'll let you guys go. My silly bell that doesn't work. Equals x. Long story short, we're going to go plugging in 9 sine squared there. We're going to plug in 3 cosine there, and we're going to see if trig will let us solve. Does that make sense? Yeah. All right, cool kids. Thank you so much. I'll see you tomorrow. Worksheet's not due tomorrow, but if you want to peek at it, you can play around with it. But otherwise, let's just work on getting everything ready to turn in tomorrow. Sound good? Bye, Joyce. Bye, Jackie.